Well, in this image, we have a small table about values. Values of what? Of what these values? Remember it, and what is that coefficient called, or that property, or that constant? Because there are several numbers. Numbers of what? What were these? What is that called? That we were studying the classes in the previous class specifically. Since they are numbers that in some way reflect the power of a group's adder or attractor, per effect. Then we have here the constants of Hammett. This is, sorry, thank you very much. It was the constant of Hanch. I was also confused. Exact. It was already for effects. Let's see. Hanch, see the effects. Hanch, see the lipophilia. Hammett, see the electronic effects. Question. What did a positive? Yes, perfect. Which brings lipophilia, and a negative value that brings hydrophilia. Question. Why then can we have different values? According to the reference system, says the aliphatic system and double-ematic system and WW. What can you tell me about this system and this system? And then we are talking about an aromatic system, PI enriched or deficient. Very well, then we have an aromatic system, pi deficient, delta plus, and we have here an aromatic system, pi enriched, delta minus. See how there is a certain correlation, but the numbers are not the same. They are not the same. He's saying, depending on whether we have the system pi enriched or pi deficient, so much so that there are some even that have opposite numbers, and then giving a fine explanation for each value would require doing a slightly way more detailed analysis, a quantum mechanical analysis. But let's see only the values we look at. Let's look at the aliphatic part first. Now here, which is remember that here is the methyl alone. What happens is that this is a methyl, and this that is down here is a methoxy, the methyl 0. 5 is the one that brings more lipophilia between all these that are here. Why does methoxy bring a similarity? Because it turns out that it has an oxygen, so to speak, in between there, which contrasts, makes it lower a little in value. But as you can see, the ethers are lipophilic, then in general terms, never forget that an ether type fragment in the structure, an ether fragment, will always be synonymous with lipophilia log P high. That is very useful when one wants to design something lipophilic, which is a fragment incorporated in the structure. Well, I think that with this they have already remembered, and now only to say that the most hydrophilic, or the one that brings the most hydrophilic with the reported value, would be the O, because we do not have the report, neither of the primary mine nor of this nitro group, but the nitrous, as you can see here, says negative OK in an aromatic ring and positive in an electrode ring. Then one says, well, but with what idea do I stay? Be careful with this, and I'm going to highlight the nitro groups. Stay with this idea, the nitro groups in general also bring lipophilia. They will tell you that a nitrobenzene is not soluble in water. Okay, the benzene is not soluble in water, but a nitrobenzene is not soluble in water either. And one says, but a polar group? Yes. But how curious, no. It does not bring hydrophilic. The nitro group brings lipophilia. And there is another problem. M. The nitro groups are also characterized because the nitro groups bring toxicity. It is not a very friendly group for the design of drugs. It is not a first-choice group. Let's see if you remember from the first class. S. Remember that you are going to be evaluated also for that. So I hope you will review what other type of group in general, one rarely incorporated a bioactive molecule very well. That is electrophilic. N. General electrophilic as an aldehyde, you will not find that in a drug, except for very rare exceptions when they are stable. They have occupied themselves in the industry of aromatizers and flavors. Another type of elo, electrophilic, a chlorine of acid, for example, that is super reactive. So no for any reason to smoke a valent elastin with what you catch at your pace. Perfect. There you are then, you remember. And we are going to do now. The following. Look, you will say, and these values can be obtained from somewhere. They are reported? Of course they are reported. They can be calculated with computational tools. But look at something super simple. Let me open the ChemDrone. So for example, if we have here the benzene, and here, next to the nitrobenzene, we put 3, the benzene, the nitrobenzene, and very well. And now, and then, let's see. I'm going to maximize this a little bit so that it looks better. Look. In the other. Then here in view, we are going to show chemical property window. This is a fast, direct way of having an estimation. Then the block paste, double-click, paste, double-click, paste. We already have a fast and direct estimation quite good. And here, in the value that you have to look at, is in the C log. PC log P is the lipophilia, according to the ChemDrone algorithm 2A. 1. This other value with the nitro group, you notice that it is also lipophilic. You will say when it is lipophilic, everything that is positive is lipophilic already from 0 up 1. 9 approximately, that is between benzene and nitrobenzene. Log P, lowered 1. 5 because there is an O that counteracts the lipophilia of the compound. The other variable that we are going to occupy and that can also be obtained from here, or from any other way to calculate, is the one that says her. AC, Mr. or molar refractivity, obtained also by ChemDrone or calculated the molar refractivity. That is what it is. That is the C of ChemDrone. But Mr. Molar refractivity, that general idea is that this parameter is occupied a lot. It is already occupied a lot in medical chemistry. The molar refractivity has to do with 2 things. It tells us how big the substitute is, the group, or in this case, the whole molecule, how big it is. Therefore, it has units of molar volume. Okay, it is a measure of the molar volume. But this is multiplied by an electronic coefficient. Then it is not only the volume, it is the volume. And something else, it is the volume. Plus the ease that the molecule has to polarize, that they have a double description, the volume. Plus the ease that the molecule has to polarize. Then ask which one has already. Okay, that is the nitrobenzene. Because here we calculate the complete molecule, but of course, but it is due to the nitro is not true. Then 3. 3. What does that mean? That this molecule, although it is true, it is more voluminous because there is a different hydrogen group. But at the same time, it is easier to polarize. It has greater ease to experiment with isometry. IC polarization. That means then having that value, so they have at least those 2 values. Top are super important. And there is another additional value from here that I want to highlight, which is the TPS should be in TP. The list of here, TPSA, in 20, outpercent, in the back, 3. It is also an estimation of the polarizable surface of the molecule in angstrom squared. Then a measure. Now there we already have 3 variables to execute, because there we have a surface, variable 1 of volume and polarizability, that is, an hysterical and electronic, and the one of lipophilia very well. Ganelin was a very important medicinal chemist of modernity, was the one who discovered the cimetidine, the first agent for the treatment of gastric ulcer. When he asks him if there is any unique discovery that, in his opinion, Ion carried out the field of medicinal chemistry more than any other response, he would go to the 60s to the work of Hans on the importance of lipophilia. I think he changed the way of thinking about medicinal chemistry. That the application of an organic physical-chemical approach to the analysis of activity structure has been very important. That is, we have that the importance of Hans is that as well as Hammett defined, as you will as Hammett defined. Remember the sigma parameter. Hans defined the parameter pi, and all the molecular properties in some way those two descriptors contain information of all the properties of a molecule, properties of structure, of volume, and electronics. Then that's what we want to characterize the molecule. Listen a global way, and with these two simple descriptors, it can be done a lot. We are going to continue then. Last week, someone had asked me, but why do we have to occupy Elisa's and logarithmic account? Why not direct as the direct does not give? And now we are going to see why the hypothesis of Hans is that we can explain any process of drug-receptor interaction. In this way, thinking that the molecule, the drug comes from a diluted medium, and that it has to have certain properties that allow it to go through biological membranes. And here there are two possibilities. Some, that it is not able to go through, for example. You can tell me when it would be very difficult to go through. There are two possible situations when it is already size, if the size can affect. And of course, when it is very polar, we already see that it bounces. But look at the issue of size today. It is also being put on the table of judgment, because it is seen that there are larger molecules that manage to go through because they bend in the space and their topological polar surface. What we just showed is reduced if there are molecules that have three-dimensional bending, but there is another p-dimensional bending. Problem. What happens if the molecule is so lipophilic that it always remains in the membrane? Then there is the second situation. There are molecules so lipophilic that they are so attached to the membrane, what is called a family of certain compounds to reach an action site will have an optimal range of lipophilia. An optimal range of lipophilia example. You have heard that cannabinoid receptors are in fashion. For cannabinoid receptors for a long time that is being talked about and has had an irium come. That because at the beginning there's a lot of hope has seen that, for example, for epilepsy, it could serve, but for other things, not for a molecule to be binding cannabinoid, it has to be high lipophilia. Hydrophilic molecule has seen that they do not serve. The other way around, if you want to have, for example, a diuretic cosmotic molecule type, a molecule that helps to excrete as much liquid as possible, are hydrophilic molecules that can be excreted by urine, that has a direct effect at the intestinal level. But if it is polar that gives the intestine and helps the intestine. Hydrochlorothiazide could be exactly hydrochlorothiide, is a very good example of a diuretic of specific action, and that is quite polar. Well, then we have that the molecule will have an optimal range of lipophilia that you are going to determine, and you say and how, because it turns out that as a general rule, This has been seen that the biological activity with respect to the log P is still an inverse parabolic distribution type. Therefore, we can know more or less how much this optimal range is having a maximum value. We then need to know what is the optimal range of the family that we are designing the molecule when it crosses the membrane. We said that there is a percentage that is retained in the membrane that is called what is retained in the membrane union. Well, in a specific union. Perfect. And what does achieve to the target is the specific. Okay, we have that the total union is going to be the sum of the inner specific union plus the specific union. Now, someone will be able to say here, and this image is quite good, because what happens if there is a transporting protein not true that allows the molecule to flow more easily from one place to another? There are certain proteins that when they receive the molecule, they turn and make the compound enter. Well, obviously. This is a simplification that cannot explain all the variables in a gain, but we have this, that the movement of our pharmacists to get to their specific site can be explained as a partition in two phases, aqueous phase, lipophilic, and the hunch hypothesis. Is this the classic kinetic law for any molecular movement that is? This equation was not invented by Hunch. This is a kinetic description of a process that says that the rate of response, depending on the time, is equal to a constant by the concentration by a constant case of x. To see this, that is here, the probability, the rate of response, depending on the time, is equal to this letter, a OK of RDT, is equal to A, which is the probability that a molecule reaches the site of action in a time interval. The probability. The problem here with this is that when we say the probability, that is a concept that, chemically speaking, is an abstract concept. How can you make that happen to be a number, the probability, to something specific? Then we have to associate the probability, or rather the product of the probability multiplied by the molar concentration of the compound, have to associate it to something specific. Then that is what we somehow want to explain. Okay. Then the rate of response depending on the time, okay, from R to dt, depending on the time, is equal to this probability already by time, concentration, okay, and by the constant of process equilibrium. Well, it turns out that that looks so complicated, and you say we are going to see differential equations, then no, because it turns out that the rate of response is depending on the time, the rate of response, depending on the time given that the administration of the drugs is spaced with specific schedules. For example, a drug is administered every hours, or every 6 hours, or every 6 hours, every 4 hours, for example. Antivirals, such as acyclovir, are every 4 hours. Not everything is every 8 hours, okay, but the rate of response, depending on the time, it turns out that it ends up being something that in practice always gives a constant value. And on the other hand, when we talk about that, the rate of response depends on the probability multiplied by the concentration. Well, we are going to say that how much is that concentration that generates an effect? Who define? Ness, that we cannot speak in terms like that. A concentration in the cell, in the plasma, dependent on the patient, no. But when we talk about concentration, we have to talk about something specific. And here he said, well, the concentration that generates an effect, the most standardized and objective way to have a value for that is to assume that for a certain drug is its IC50, the concentration that generates the effect, or that generates the effect. 50% of the answer, or the inhibition, that then already, if you look at this, it is more or less simplifying, because we are going to have here that this is constant the rate of response, depending on the time we are go. In to have that this in some way, we are going to have to go from the abstraction to something more concrete. And this would be our IC50, and K is the constant of the process, but this is also another constant then. This is already what was said. First, it is objected that the process is more complex than a two-phase partition. There are many intermediate partitions, of course, already. But this is a model. There are multi-component models. Yes, but why complicate? If this already works and explains quite well the activity of a family of molecules, because I say that the process is more complex than a partition in two phases, well, you know that when the drug goes by oral route, the drug by oral route first has to face the problem of intestinal absorption. Then it has to face the hepatic metabolism, and from there it is distributed by the plasma, and it will reach the action site. In some way you are going to space that, particularly the hepatic metabolism is another access route, the intravenous route, the intranasal route, the sublingual route. For example, the whole hepatic metabolism is already skipped well. On the other hand, here is the problem we must correlate to with some experimental variable. Several researchers, such as those who mentioned here, already spoke that it was possible to rationalize the probability that a molecule reaches its action site to such an extent that they came to say that the probability depends on the mobility rate of an organic compound. And what is the most similar physical and chemical variable to that, to the mobility rate of an organic compound, to the log P? And you probably know it from biological experiments. The compound has to be dissolved so that it can move and reach the target, and in which one generally dissolves organic molecules to do biological experiments. Exactly that is one of the most used. It can also be in ethanol if the compound is more polar, and if it is not super lipo, we have to use dimethyl sulfoxide or DMTO to be able to dissolve the compound and have that thing T. Hat has an adequate, not true, an adequate mobility rate, and therefore increases its probability of reaching the action site. Then, as you can see, this is nothing more than a mental game to be able to rationalize this probability and say, okay, that probability corresponds to log P, and instead of using P, says their Hans developed a comparative substitute constant called pi, analogous to sigma of Hamlet. Then Hans said that the probability that something reaches its action site depends on the lipophilia O, F, the fragments that constitute the molecule, because pi was the lipophilia of a fragment E, of a fragment. Then the Hans hypothesis is that the probability for it to reach its action site is a function of the lipophilia pi of the fragments of the drug, of which fragments of all the fragments that are relevant for the activity. Okay, not necessarily all the fragments will explain the activity, but there is always a set that is the most relevant, and we have that according to the hypothesis of Hans, and the probability is a function of the lipophilia. And this probability, according to Hans, follows the equation. What equation is this when you see this type of graphs like this? Exactly. Then, look how interesting we have here. The hypothesis of Hans is that there is a Gaussian distribution of what thing of the probability, and in other words, of the lipophilia for the drug to reach its action site, T. Hat this is the Gauss equation. This pi is not the lipophilia pi. That is the numeric pi. Okay, that pi, that is. There is 3. 14. This sigma is not Hamlet. That sigma, if you look here, is the amplitude of the curve, and then we have that sigma gives us the amplitude of the Gauss bell we have, on the other hand, that in the part here is the exponential. LOK, the Euler number. We have the variable x, we have the minus mu, that what is mu is the point in which we have the maximum in the x-axis. For example, here, it says mu 0, because all the bells have the maximum in an x equal to 0 except the green one that has a mu minus 2 here, because it has the maximum in minus 2, is that mu value that is up there. Okay, then we're going to take this, but look at the following. This amplitude, or that value, sigma, that which is there is a constant pi, is a constant, and it is a constant again. Sigma is a constant, mu is a constant, then it can be grouped in some way to get something simpler. Okay, and x, we are going to tell ourselves then, function of what is this for us? This is the behavior or the probability that the drug arrives. The probability that the drug arrives is a function of pi sub x. Okay, then there is a maximum value of the lipophilia pi 4. The drug to reach its site of action, okay, so that it reaches the maximum probability of arriving then in the x-axis, and therefore our equation would be transformed into this and this that I am showing you here. You will see this is not as exact as a classic mathematical demonstration. No, this is obtained directly from the hunch papers. Hence, you're going to give the first hunch papers to the paper of the year 64 that I showed you in the class. One of the previous classes there, he makes this reasoning that I am trying to explain here. Okay, and exposes all read. In this way and places the equations in this way. Then he comes to say that the rate of response, depending on the time, depends on the probability. Then it is here that you see here, this probability is a function of what? Thing of the lipophilia is a Gaussian function of the lipophilia pi. And that is why here now I have the equation of Gauss, where I only know that what was done here, a term was grouped, a constant. Remember that we were just seeing that there were several constant values, okay, above the value. P another value, the mu that would be the pi 0, or the pi of the optimal lipophilia. Okay, divided by another constant, and the c, that is here we had already explained, it will be our IC50, and would be enough to say here that this is also a constant that we are going to call Q. The rate of response depending on the time is constant then. If we have all this that we can do to clear the equation regroup terms, but we would lack one last conversion, and here comes the genius of Hans. He says that the constant that we have here, case x, I can replace it by the equation of Hammett. Then this that is here, we can replace it by the equation of Hammett, and we are. This is the part that I want to. What the equation of Hammett showed in this term. They remember kx divided by h, that is the same as saying the logarithm of case x minus the logarithm of case h, equal to this row, that we already know that it I is worth 1 for aqueous equilibria by sigma, which is the constant of Hammett, okay, that is. It is the subtraction of when the acid that was the reference system has the substitute x minus the benzoic acid when it does not have it. A substitute. Okay, then we can replace ourselves now. This, and if we take the kx, it is not true. That is also convertible here. Terms will simply move from one side to another, 1 divided C1 divided, and C50, as an exponential is cleared. We apply the natural logarithm first, and then later we convert the natural logarithm to the logarithm on base 10. From there comes then this of log of 1 divided by c, 50, or is the same as that p and c, 50 then. Now you see it is there, it is implicit in the supposition of Hammett. So from there, it came because we have to occupy p and c. 50p and c, 50 is equal to what is equal to a sum of t. Amps is equal to what? To the contribution of the lipophilia. Allows me to move a second further to see the other variables here. P and C 50. Let me write it this way because that's how we are going to see it always. P and C 50 is equal to a contribution of the lipophilia, or that there a contribution of the lipophilia, or here a contribution of the lipophilia. There are these two. So there we have the lipophilia, an electronic contribution, and a constant of regressions I have here, P and C50, equal to the contribution of the lipophilia plus the electronic contribution. And this is the base. Question: according to this equation, as it is written here, it is convenient to increase or reduce the lipophilia for the comment to decrease the. What can you tell me here? We are saying P and C50 is our variable y, and here is y the dependent or independent variable, y independent, but it is this biological activity P and C50. The dependent variable already, the dependent variable P and C50 depends on what? Depends on the lipophilia, depends on the electronic properties plus anything else that I can incorporate into the equation. And there is the key. Therefore, I repeat, if I want the biological activity to increase according to this generic equation of Hansch, as it has to be the lipophilia, here it says minus k by p squared plus k. And that is because if this term is negative, it will subtract the linear contribution. So the point is, and how do we know how much is the maximum value? We can graph this, and we are going to find that there is a value of t. Lipophilia, that makes this maximum. And if we exceed that maximum, that is going to happen, the quadratic term exceeds the non-quadratic term, making all this negative, and therefore we subtract the global value of the biological activity. In other words, we never forget this. We never forget that the lipophilia is always having something in this. This is log P lipophilia, or log P, if you want to call it, versus the activity. It always has an in. Parabolic question. And what happens if you find an equation of Hansch that does not have the quadratic term? For example, log P and C50P and C50. For example, I do not know. I'm going to invent something already. 1 by log P, the global, plus 5. Imagine a short equation. Imagine that you arrive at this equation. I am already interested in the part of conceptual reasoning. What does this mean? That to increase the biological activity, that I have to do with the lipophilia of my compounds to increase it or decrease it, to increase it, because the coefficient is positive 3. 1 positive, then if I increase the lipophilia, it will increase the P and C50 already. But that equation is an incomplete equation, because how much can increase the lipophilia? In the paper, infinite and important, and the mo. Ray, I increase it. I will have a better P and C50. Then that is going to take me to invent unreal molecules. What happens? I am going to invent a molecule with 20 benzene in the structure, because with 20 benzene, it will have a giant lipophilia, and therefore it will give me a wonderful P and C50. But that is not real then. When you obtain equations of this type, you have to be very cautious because they are working in this range of lipophilia. They were left with an equation that describes only that part of the curve. Then one says, of course, that how I know where the cut is, how do I make the negative quadratic term appear? I have to evaluate more molecules. That is why the things with few molecules are difficult, okay, because we have little data, and so that they go reasoning how this thing is, and a final observation. Already a final observation. A final observation is that in this equation, you can incorporate more terms. That is, this equation that is here is a generic equation where you can incorporate any other type of term here. We only have basically incorporate two terms, lipophilia and Hammett electronic property, property hysterical or not true of the lipophilicity of the compound. Then, how many more variables can we incorporate? Then, how many variables can have a QSAR equatio? And then, someone can say, I can incorporate as a variable, for example, apart from lipophilia, and apart then they are valid descriptors. The lipophilia, the P, or the squared lipophilia, is also another variable more or the same. But with pi of specific fragments instead of the global lipophilia, I can have electronic properties, okay, like the sigma. I can have the molar refractivity. Remember the molar refractivity. I can have the topological polar SUR. Face of say, invent whatever you want. I can have the energy of the orbital HOMO. I can have the energy of the orbital LUMO. I can have the global electrophilia omega of the molecule if I can have the chemical hardness of that. A molecule and follow. I can have free Wilson descriptors, that is, I can have X sub I equal to 1 or 0. If we can have mixed everything, then how long it is not true. It has to be my equation. And there I ask you the question. Of common sense, it is better to have QSAR equations, long or short equations, that you want in large parts as a general idea. I know that all this is a bit flexible. There are always debatable things, but the general idea, if there are more descriptors, those parameters among themselves, we have to make sure that they are not correlated with each other. It could be that under certain conditions it helps to have a large equation to give mechanical explanations, but the problem of having a very large equation, and it has not happened, is that a very large equation does not solve. Cost much to consider the weight of each descriptor in the equation, okay. That is, one sees many times descriptors with similar coefficients. Therefore, the question is, what is more important? The lipophilia or the surface, the refractivity or the electrophilia is understood. Then when the equation is very large, it is difficult to consider the effect and the importance of each descriptor in what thing in the explanation that they give of what of the biological activity. If finally what we want is to explain the biological activity, then my advice is that it is better to have shorter equations, but more equations. And then it is better to have a larger number short equations, but more for the same family of molecules. The other thing is that I mentioned it already, only, but there, where we are going to go, working after the workshops are not going to be recorded. That is part of the work. It is not true that we are going to D. Oh, here, in a practical way, moving in the room, and the other had to do with I. Do not go to have collineal descriptors. Okay, then they must be avoided. I am going to collinear descriptors. I explain. Imagine that you have the clock calculated by ChemDraw, and someone says, but I also calculated another lop. Okay, there is a website that calculates with another algorithm called a lodge. And they put them together in the same equation. No, because they are collineal, okay. Of course, they are different values because they calculate with different algorithms, but they are descriptors that the two of them are X script, explaining to me the same property, only that with numerical variations. So it cannot be done. We have to avoid. Very well then. With that, we have already moved forward a bit. This is the explanation that Hans finally gave, where the generality was, because I know that mathematically this is like when one demonstrates the equation of T, the equation of what is called the equation, the great equation of quantum chemistry, the equation of Schrödinger. You know that that is finally taking the equations of Newton to the quantum mechanical scale, and the passage from there to the quantum mechanics is not so direct. It is not an absolute demonstration. There are certain assumptions in the background. Here, the same thing was done then. After this, I do not find it so exact. This is a hypothesis, and it has worked well so far. And the hypothesis is that the activity is better explained in logarithmic terms, its behavior for a set of certain descriptors, because this way we obtain an equation that explains T activity better in logarithmic terms. If you put the value here, not logarithmic, it will reach anything. Toxicity. They were studying different benzoic acids, what biological model they had, that with what biological model they were testing in mosquito larvae. That is, they were testing how toxic these compounds were in mosquito. Oh, larvae benzoic acids with different substitutes. Okay. Then, what end does it have to create something that kills mosquito larvae? Well, two things. First, it could be right to look for an insecticide, and second, it can be a toxicity model. That is, this can be a model to test drugs better. Also, a mosquito larvae is quite sensitive to environmental conditions. Then if a drug kills all mosquitoes, well, alert here more than quite toxic also at a human level. Well, what he did here is how many molecules were studied. Ed, how many we're going to study in the workshop 10. And he has 14 functions here, 3, 4, 5, tri-iodo. What does that mean? That here is iodo, iodo, and iodo, that etc. After the iodo, para iodo, etc. That is, we have with iodo, with chlorine, with hydrogen out there, to walk there is nothing with methyl, with fluoro, with methoxy, with nitro, and with alcohol, then super varied, already super varied, tried all the possible combinations of this node. There are only 14 molecules. So let's go here now. First descriptor, that is, first descriptor in a column is missing. That here I do not have it, but they measured it. It is also missing the column X sub 3. That is, X sub 3 is the previous value, that is X sub 2 squared. That's why they want to raise this term to the square for what he did, that Hans does not highlight the value. I do not have that column, but they did it there. First, we're already going for x1. What is this? Okay, very well in this. A sum of the coefficients of James of the substitutes that are here I, and says, the sum is not a sigma, is the sum of sigma, k sigma, and then, when there are 3 iodo, the sum of 0.98. What does that mean? That they do those 3 iodo that exactly 3 iodo are quite electroattractors. 0.98, okay. 3 iodo together attracts more than 2 to see where it is 2. The one that follows 0.72 iodo. You see that is perfect. We go her. A to the second value here next to the sum of the P3 toy. 73 question that they do not find high or low high, that is 3 iodo. They provide a brutal lipophilia 3.3. 7. Only 3 atoms within the structure, so do not forget when one places iodo. And then I insist, here it is not the value, but they wanted this value from here. They raised it to the square, and that this that is here is the log pi, that is 373, is the sum of this value with this value, and with this value is the lipophilia of each fragment, not of the whole molecule, only of the fragment, is the lipophilia only of the fragment. Yank is the POA okay. Remember that P is the lipophilia of the fragment, it is not the global log P, and it turns out that yes, because look at this value that is here, is the lipophilia of these 3 fragments, it means that the whole molecule has a lipophilia superior to that, therefore perhaps that it does not comply with the rules of living. And it happened, how much was the limit? 5. I do not know this well. Then it probably does not comply with the rules of Lipinski. But that is not true. It is the each sum of pi, they raised it to the square, and they had a variable x3 for what to do that. Someone can see if we are not working there with something collinear to have the same thing again. But squared it will not be collinearity. And I just told you that we cannot have collinears. Yes, but remember that if we have collinears, yes. But remember, a p squared that will describe the full lipophilia curve, and therefore we are going to know where the maximum pi is, the one with the negative term. For that then the value pi elevates it to the square to be able to test, more or less, where is the limit of the parabola? Okay. Where is the maximum value? Then we have that later. And here, this is as you understand. This I took it out of the original paper. That is why it looks so bad. Think he. Right? It is not even understood. But here, and here is the observed. This is the one that interests me, okay. This is the PC50 observed, and this PC is clear. The observed is our variable, y. The calculated when they get it. When you create the excursor, as this is a paper, and it is already. Yes, that is why this work is very close to the observed. It is very close, and only with 3 descriptors, there we can see the genius. And this, with very little, was done a lot. They were discovering something that no one had. Ever done so, there is the relevance of this, and not even with an ultra-complex mathematical analysis. Because now, if you have yx, that they can do multilinear regression. That is what we are going to do. Multilinear regression. Then see here on the side that what is this delta log C? The residual, and this, that is here, is the residual that is the res. How much was the maximum tolerable of the residual? Exactly. Exactly, ideally the residuals or deltas have to be less than 3 times the standard deviation. There was another criterion exact. There is another criterion that is more approximate that says that they have to be less than and 1, but that is very approximate. We have occupied it. When one quickly wants to detect an anomalous value, okay. But the fine term is this residuals less than 3 times the standard deviation of the model, we go there. figure n with multilinear regression. That is what they found. They began to play and report all these combinations obtained. That is why I tell you we can have several equations, of course, for example, P and C50 equal 0.5 and HT equal 0.5 times prime 15. That is the first equation. One equation, two equation, three, equation 2P and C50 equals 0.15 times pi squared plus 0.2. 5 times prime 15, and equation 3, the same, very similar, but plus 0.7 times sigma plus 130. Sigma plus 1, 1. 6. Almost we have reported the value of r squared for the three equations. Remember that there is a difference in docking. I know that this is more abstract already, but that is where the importance is, that they are able to interpret the result. Then the question is based on these three equations. We are able to, through some of them, know what the value of the optimal hypothesis is to create the maximum toxicity. In this case, they were toxic molecules, not certain, against mosquito larvae. Then, with some equation, we end. Oh, what that max? Yes or no? What do you think what equation should be seen? The ones with pi squared. From 12 to 3, some of them will inform me the maximum or pi always grows. Here it is, positive, exactly, it always grows. What does that mean? We are not able to give with the negative term. Why not? Because there are hardly 14 molecules. That is, we have a short universe of molecules we're not able to give with the term of optimal lipophilia. Okay. Then it is a conclusion. The second conclusion is that at high rates at higher lipophilia. Not true already. We do not know where that certain point is already here then. At high rate at higher lipophilia, at higher log P, or at higher lipophilia pi of the fragment, because greater activity, greater or greater, P and C, 50 greater, P and C, 50. And that means less and C, 50. If they did not have enough lipophilic fragments within these models to get to this other extreme and find the relative, it could be clear that they lacked to cover a wider range of R. Of course, they stayed in the first part, where they stayed in this part, because they remember that in this part of the parable of activity versus lipophilia, in this part, what does the curve look like there? Curve? And it looks like a line, so as the curve, and it looks like a line already in all of a positive term, and they did not have higher. The explanation very well. Finally, I want you to tell me then now, and what happens with the electronic properties to have a good toxic against mosquitoes? Okay, I have to be lipophilic, and what else, as it has to be the electronic property of the molecules. The only equation that speaks to me about that exact is the last one, and that is the point as the sigma has a positive coefficient. It is convenient to have an electrode group. To experience no, because positive, we are a bad electric attractor. Yes. Electric attractor example, name me. At least one. Very well, that is how the great electric attractor is not true example. A nitro group, it is convenient to have an electric attractor that removes electronic density. Okay then, on the basis of that you are already designing B. But how do you design now in a slightly more abstract way than in Free Wilson? Because they are no longer concrete substitutes, because something electric attractor are many possibilities. I can take it out of a table. I can invent an electric attractor group example. Trifluoromethane was not in the previous ones. I can propose it. I would have to measure the value sigma, and see what value of biological activity it gives me. Okay then. I propose based on the last equation, we calculate what the toxicity of this molecule is going to be. Then based on equation 3. And there you see that this is now becoming a kind of poetic as well as an explorer that I can do because use it is no longer free will, it was super specific. This fragment, or this other node, this yes, this node, but here we can already speculate, and therefore as it has to be something lipophilic, an electric attractor, there you to all those previous knowledge that we have already studied, and you say we could have, for example, a trifluoromethane because the lipophilic and attractor. How much is the first? How much is the lipophilic already of this fragment? I need the pi. Then we need two things. We need the pi and we need the sigma. How do we do that? Look now. Let's go over here so that we can do it quick. Clywell. Then we are going to calculate here. We erase on this website, Peter Ertl. Commande. We draw the trifluoromethane here, then there and here. Our trifluoromethane has 3 flowers. Trifluoromethane there. It is, and we have to say that this is the R. Then the R, then this is the calculation group and the sigma I. 547 and the pi. What happens is that it says sigma m and sigma p refers to sigma in meta or in para, and how were we para? Very well, and at 0. 647. I know that it does not come from the tip, but I am going to write it down from there. We go here 0. 647, and the pi 180. Captain toot, nitten orto tari, captain packen steel. There it is, then we have the value shunt. Therefore we have that the PC50 based on this, the PC50 from the last equation, the PC50 would be equal to 0 gas. But B. Plus 0 dot dapsi packen posiganity kadiga konen into at C. 169 plus 0 dot T isn't it 2 by more the very good. The called what is called that is not true, and how the intercept of the line plus 1. 557. Well, there we have then the values us. You can see, and let's see how much our PC50 gives us predicted PC50. Let's apply the calculator. Well, then, the sum is 2. 15. And that is the PC50. Thanks, then, exactly how that was done. And very well, then the IC50 is 10 raised to minus 2. 15. Very well, and that in what I'm going to see, because it turns out that here, when we do not have anything we are going to be cool. And of course, because now we have to say that this expressed in this way is not very reasonable, we move it with more 123.7 millimolar. No, that is, if you ask me about mosquito toxicity, if you are looking for an insecticide, okay, you have to occupy that concentration, and if it is not toxic for humans, there is no problem. A certain one will probably spray plants with this. It will be spent more mass, then economically, it may fall the industry due. Not like it because we need more mass to kill more economic spending very well. Then we reach a value of 7 millimolar of the toxicity for this compound then and there, where you say, but teachers, that maybe we can get a better effect before I had seen that the good ones were good, remember. Then I could have yodo here and there again calculate and see how much it gives, or we could have this same group 3 times. So as a task, you have to calculate how much they give those variations that is already doing things is to be designing something from a new equation. Well, then in these minutes that we have left, we are going to see some concrete examples that we already have, but first some practical questions look apart from the numerical equation we have to graph something. Yes, because even this little thing here, I like to leave these things so indelible. That we have to do the monkey, the graphic of what thing that would be this. Perfect. Then this would be the PC50 we're going to say here. The XX is the PC50 experimental. And the Y is the PC50 calculated. Remember that experimental is the same as observed. It is exact with this we verify, as is, that the model exact. And there are several very fine things to mention. For example, here obviously this line is more or less good. The distribution of points is appropriate. There is a good distribution of points if approximately the line arity, and you will say good for publication effects. It is enough to say that it looks more or less good. No one says it in a more specific way, that is. There are variables that one calculates for this, and then one says if the line is approximately good. But what happens if in reality, look what happens if in reality the line equal x is this. This is the line equal x. That would be the ideal situation, not true. And then, now, let's be honest, this was the same as the line equal x. No, it is deviating now, you will say. But there is certain tolerance. Yes, how much good? The problem is that we cannot deviate a lot, because if the line deviates a lot, 2 things. How is the prediction for compounds with low activity? Those who are from here backwards. And that is, those with low activity, those with low activity. Yeah, but look at this part. It overestimates the calculated value. That is, it predicts the bad compounds as if they were better because we are above. And to the good compounds, it predicts them as if they're worse because they are below the line. It is understood then, that is the first interpretation, that the line with this type of deviation. Then it is not true. We have to adjust hopefully that it is the most similar to the line equal x. You would say enough that it is parallel. Hopefully it is more or less within this range, because it could also obtain a line equal x of this type. What happens if all the points they gave here, and it gives me a line like t, it is parallel to the line equal x, but it is up here? Then what does it mean that it is overestimating all the predictions? And it does not work no matter how very parallel it is to the line equal x. And before giving more explanation, look at all the other models are bad modeli. Else, this is obviously bad because it has an inverse correlation. And someone can say, but professor, and this one, because it is bad if the RD09, because look here, in reality, we have the activity would explain itself better if I separated the compounds into 2 sets and look for a regression for these and a regression for these others. understand we have two families of compounds. Well, this, here, the R06. But in reality, there are three lines that go down this. In reality, it also adjusts us to a line that looks exactly then. This looks more like a semi-logarithmic curve, that is. And the last one has an R of 0. Because it is a parabola, then now, I am going to give some additional values for this line up here. Then the question that arises now, my QSAR model, how much can be deviated from the line equal x? The answer is the deviation established according to literature, the deviation of the ideal. The deviation has to be less than. It can be estimated in several ways already. This less than 15% look we can estimate it with, for example, to say that the slope of the line has to be less than or equal to 1/15 and greater than or equal to 0. Yes, but we are going to have a single slope. When you graph this is not true, we are going to have a single value for this line, the slope of this line, I mean, because the slope of this is not true. The slope of this line has to be in that range 0.85 to 1 and 15. If that is fulfilled, our model is quite acceptable. Other statistical parameters can be calculated apart from that. If they can be calculated, and it is what I had told you at another time, that of the total of molecules. Exactly the training. And the test set. Obviously here, Hunt had few molecules, then all were training set. Then, as all were training set, the R squared ideally has to be greater or equal to 0.8. If this is fulfilled, then we say that we have an acceptable model. There are other metrics that can be calculated that are already more specific, and we can see those later with some concrete example. For example, you can calculate what is called the May, or that is another thing that the deviation of the residuals can also be calculated, another parameter called the sum of the standardized residuals, and you can make a graph with that t. Oh, then there are another series of parameters that can be calculated, because sometimes it is not very clear if the model is good. Sometimes when we are in the limits and one says, but how? With another variable, I argue that they will laugh when they see this. Mexican lemons to rescue. Then they have to see the Mexican lemons with the QSAR, and it is published there because it turns out that to make a call to attention to the community, that is, more than making fun of what the authors are looking for, making a call to all the people who made QSAR, because it turns out that absurd equations are found. I have seen equations, for example, with descriptors, they have a topological name, but then there A is not a way for those descriptors to explain the biological activity. That is, the mechanism of action. As I, with those descriptors, I explain the mechanism of action, is very difficult. But look here, it says that the it says that the greatest amount of imported lemons from Mexico to the United States is seen that there is a decrease in fatal traffic accidents over time, and with a square root of 0.97. Then, this means that the equation went very well, but the correlation is absurd, and that is, It is not that the accidents are going down because people are importing or eating more lemons. Then what you want to show there is that in reality, in QSAR, a lot of care, because sometimes you can get correlations of whatever it is, and it gives a good square. But the lemon QSAR, and then we return here now. And as I tell you later, we can see other metrics only to finish now to conclude some small examples with the case of lipophilia. Well, we already explained the Hans equation. We already explained what lipophilia is. We already explained that lipophilia follows a parabolic distribution inverted with respect to the entire family of compounds. And that if I have an equation that is not quadratic, we are in the And here you can tell me what the mechanical interpretation of that. Already, well, here's where you have to integrate everything we have seen. We have seen pharmacophores until tiredness, and this has been repeated a lot. That is excellent. And then the first thing to remember to these were people from thalassotomy very well. There is the pharmacophore ring response. Play for biological activity, that biological activity good and antimicrobial, and we had said that they inhibit enzymes responsible for the synthesis of the bacterial cell wall. And those enzymes have a nucleophilic serine. That is covalently linked to the beta-lactamic, particularly to that position. And in that way, the enzyme is inhibited. Okay, a serine that attacks right there and then. It was to remind a little, but it is not necessary, we said, to know the protein to make a QSAR study what they found. And in this way, the amoxicillin was designed. It sounds like that amoxicillin. And why? Observe the following. We are going to draw what amoxicillin has, but what the thing you found was this, that for beta-lactamic antibiotics, because synthetic amoxicillin is not a natural product, and penicillin is natural for natural beta-lactamic antibiotics, and for some that were already being created, they found that the biological activity, remember that this is the PC50, and I am insistent on that, so that it is not forgotten, never is less than 0. 5 pp by pi plus a random intercept. Then this equation is super simple. Short, does not have more information than pi is the lipophilia of the group. Lipophilic groups, or hydrophilic, exactly as it is, they're the point. That is why it is important here to stick to the sign. It is convenient for me then to insert hydrophilic group. Then conclusion. I need a hydrophilic group connected there, and there is no hydrophilic. The molecule has to reach the target, yes, but these act on the wall of the bacteria, do not need to enter. That is why then that something hydrophilic favors molecular mobility, so that it reaches the surface where there are many electrostatic charges, ion, salt, whatever it does not need to enter. And there is also another factor that is implicit in the EQ action that we are going to see now. But the point is that when they saw that, they said, we can try this, and someone said the simplest, the most hydrophilic, a classic hydrophilic group. Which hydrophilic group par excellence? A column, H. Then if we go here, look here, aromatic, because it will be connected to a benzene ring here, this part, then that value of minus 67. I would apply minus 0.67 is the most hydrophilic of the series if it is not hydrophilic of the series. Rue then, as it is the most hydrophilic of the series, that you have to place alcohol, and within the reasons to insert it in a para position is also that it was synthetically more feasible. Then they said, we are going to connect to alcohol in the para position. And that is precisely what the amoxicillin molecule has. The amoxicillin has an alcohol in a para position that is connected here in the aromatic ring, right here in this position. So, see how interesting how from an equation it is already possible to connect something hydrophilic. And it was quite good. And not only that it was good, but that this alcohol allowed the molecule to be active orally, the amox. Ethylene can be taken orally, unlike penicillin. For example, another observation, notice that this QSAR equation was made with 20 molecules and has an error of 0. 827. From 20 molecules, we achieve the creation of something completely new and effective. I do not have the standard deviation reported here to have calculated what was the maximum tolerance margin, and with that value, you can predict the PC50 equal to minus 0.8 equal to minus 0. 445 by minus 0.67 and plus 5, 603. Then it gives us a PC50, and quickly to have value and it gives me 597, but not bad. Yes, 597 that is. We are close to 6. We have a value close to the micromolar range. Now you can say micromolar. It is not like the eighth wonder of the world. You know what the grace is, that the beta-lactamic antibiotics have a QSAR, a Mendo's tolerance margin, and they take high doses. For example, the amoxicillin. How much is the dose? It can become a gram every 8 hours. A brutal dose, you see. Then there is a concrete example that it is possible to create things. We would have some small things, but the other class, as it is little, what we have left to see the other class, we finish with that. And if the other class, we are going to be looking for our correlations of the data bar. Z, that I am going to make them